Hey guys, BuildZoid here, and today I'm going to be addressing something that's come up in the discussion of the 12-volt high power connector a few times, which is if the GPU isn't power balancing the power connector, why doesn't the power supply current balance the connector? Well, there's a simple reason for that. So here we have a power supply and our offending GPU with no current balancing. And we're gonna, for simplicity's sake, we're just gonna have two wires, and we're gonna model those two wires with their connectors as just one resistor each. Also, we're gonna ignore the ground wires, right? Like, obviously we need some way for the current to return back to the power supply, but we're just gonna ignore that because, especially with the 12-volt high power connector, the pins that keep melting are always the 12-volt pins. And there's a very good reason for why it's always the 12-volt pins, but we're not going to get into that reason today. So we're only going to worry about the wires like that, current goes towards the GPU through, not the return current. So then, and we're modeling both wires as just a single resistor because technically a real wire is obviously made up of like the connector end, and then you got the wire, and then you got the other connector end, and like the thing is like this is, this is basically a resistor, this is a resistor, this is also a resistor, but these are all in series, so that's just one bigger resistor, right? So that's that. So we're modeling the entire like pin, right? Like terminal, wire, other terminal as just one resistor for convenience. And that is a completely valid way of looking at things in this case, especially from the power supplies and GPU's perspective, because, yeah, like if you soldered the wires from both ends, they wouldn't be able to tell the difference. Anyway, so for convenience, we're going to go with a resistance of 2 milliohms because I don't know what a realistic resistance for this connection is. And 2 milliohms makes the math easy for me, at least to start with. Eventually, it's going to get worse later. So typically, also on your power supply, all of the outputs are combined into one, and we're going to just go with like the PSU outputs 12 volts, which means here we have 12 volts. Now, technically, some PSUs do have forward voltage sensing, but as far as I know, it's basically never forward voltage sense against the GPU. I think most of the time it's against the motherboard, and I think it's through the 24 pin specifically, which is kind of funny because the 24 pin generally sees the least amount of 12-volt load. So that's, well, depending on your priorities, that's probably not ideal. But anyway, for convenience, we're just going to ignore that problem, and the power supply is monitoring the output voltage at its own outputs. We're not, like it's not monitoring at the GPU, which I can tell you for a fact, I think there's like one power supply that has the option of monitoring the output voltage at the GPU. So, yeah. Anyway, so we've got 12 volts over here, and in this scenario, let's say we've got 20 amps flowing into our graphics card. Well, with 20 amps flowing through our two 2 milliohm resistors, that's going to be 10 amps through each line, right? Which is also going to mean a 20 millivolt voltage drop across each line. So that means the voltage at the GPU is going to be 11.98 volts, right? And this is perfectly fine. Your GPU is perfectly happy to function with this voltage. In fact, the GPU's voltage regulator is probably going to function just fine even with just 11 volts. It's just not really going to be thrilled about it. But anyway, so yeah, so we've got 12 volts coming in, two 2 milliohm resistors. Everything is nicely current balanced. Lovely. Now, what happens if you plug in one of these two, like what if one of these connections is a bit wonky? Let's say instead of 2 milliohms, it has 4 milliohms of resistance. Well, in this scenario, what that's going to do is there's going to be 2x the current of what's down here. Right, so we're going to undo all of that. So that's a 4 now. And again, we're going to be pushing 20 amps. And what's going to happen in this scenario is we're going to have the combined resistance of this connection is going to be 1.3 milliohms combined. So we're going to get more voltage more voltage drop at the GPU. So instead of getting 11.98, we're going to be getting 11.973 repeating. volts, something like that. It's going to be slightly less. It's not a huge difference here. And more importantly, we're going to have 13.3 amps repeating flowing through the top line and just 6.66 repeating through the bottom line. Great. This is why the current balance goes out of whack, right? There's twice as much resistance here, therefore there's going to be twice as much, like the connection with half the resistance is going to carry twice the current. So this is not ideal. And so let's say we want our power supply to fix this scenario somehow. Well, the easy way to fix this would be to do the following. We split the rails over here, right? And then inside the power supply, we add some extra circuitry that basically adds some extra resistance. And then this can be another 2 milliohms. And then we're going to have extra, magical resistor that's 0 milliohms. So now this top line is 4 milliohms, the same as this bottom line, right? So now we have achieved current balance by basically adding extra resistance at the PSU. But this means that the voltage at the graphics card is going to be even lower, right? If we're outputting 20 amps, well, now we've got 4 milliohms up top, 4 milliohms up down on the bottom. So combined resistance is going to be 2 milliohms. 20 amps flowing through that is going to drop by 40 millivolts. We're going to get 11.96 volts at the GPU. Now, the GPU is still going to run just fine on this. Like, that's not really a problem, but that's because these resistances are so small for this scenario. So this is like the lazy way of this is like one way you could try to solve the current balancing issue, right? Is your power supply would basically have to have a bunch of extra monitoring circuitry so that when the GPU is running, it can detect that, hey, some wires are, there's more current flowing through these wires than through these wires. So I will now dynamically add extra resistance to the wires that have the lowest resistance. Now, the potential flaw with this is, like, let's say this resistance is really, really high, right? Like, let's say this is 50 milliohms, well, or 100, right? Like, and in this case, you would have to add like 98 milliohms down here, which now we're going to get 11.9 volts at 20 amps, because this is going to be 100 milliohms combined, right? Because we're going to add 98 inside the PSU. So basically, at some point, this method of trying to balance the current is going to break down. And quite frankly, if you're going to be adding all of this circuitry into the PSU, why wouldn't you just put an alarm that tells you, hey, your power connector isn't plugged in correctly, do something about it? That's probably a better solution than, adding a bunch of active circuitry into the PSU to try load balance your silly connector. So this could certainly, so this would be one way of doing it, is you add like a bunch of, you'd probably use like MOSFETs for this, and you'd just you'd use them as variable resistors. And yeah, that would be, it'll lower the efficiency of the power supply. It'll lower the your operating voltage at the GPU is going to be even lower than with just the badly balanced connection. This is not a good solution, and it adds a bunch of cost. So that's not great. Now, what's really funny, though, is one way you could try reduce the imbalances is just add a lot of resistance on both ends, right? Because the big problem here isn't that, like, oh, this is 4 milliohms and this is 2 milliohms. No, the problem is that this is 2x what this is. So one way you could sort of solve this current balance problem is stupidly just add like 10 milliohms on both ends, right? If you just do that, what you end up with is this is now 14 and this is 12. The difference between 12 and 14 is a lot smaller than between 2 and 4. In fact, 12 and 14 are basically going to be perfectly current balanced, just because they're so close together, right? And if you keep going up, like if we add 100 milliohms on both ends, then yeah, it's going to be like perfectly current balanced, but now your GPU's voltage is going to be extremely low again. So that's a stupid idea, but an option. So like one kind of funny thing is you could potentially load balance a 12 volt high power connector by just daisy chaining a bunch of cable extensions, because each extension is going to add resistance, and as long as it's like different pins that, aren't plugged in, like one concern is like if you plug in a chain of cables into each other, right? Each cable you add adds some resistance. The main concern is like if the same pin in each connection is the worst one, then you're not actually going to achieve anything. But if the like mismatch of the connections in each of the connectors is completely random, after a long enough chain of extensions, you should get a perfectly balanced cable. It's also going to waste a bunch of power. So that's stupid as well. But yeah, that could actually, like, theoretically, that could actually end up with current balance. It's just like your GPU's voltage is going to be very low. So yeah, so this is why power supplies don't have a bunch of like adjustable resistors inside them so that they can tweak the current flowing through whichever so that they can reduce the amount of current flowing through whichever wire has the lowest resistance. And another issue is that like the power supply would probably need some way of figuring out like, is this even like well, I mean, with a strict enough spec, I guess it could work. But yeah, like from an efficiency perspective, this is bad. Also, it's not ideal for your GPU's power delivery because the more resistance you have over here, right, assuming that you have constant output of 12 volts, well, if the current flowing into the GPU isn't super consistent, like let's say it's pinging between, say, 10 and 40 amps, right? And we're just going to pretend that this is balanced for convenience here. So we're going to go, so the current draw is bouncing between 40 and 10 amps, let's say something like this. Then the voltage at the GPU, if we have 2 milliohms, then it's going to be, you're going to have a maximum voltage drop of 40 millivolts and a minimum voltage drop of 10, right? So the voltage is going to be bouncing like that. But then if you do the like plus 10 milliohms on both ends thing, and actually just for convenience, we're just going to go 10. Actually, let's just go 10 milliohms, 10 milliohms. And so now what you're going to have is the combined resistance. So this is like combined resistance 1 milliohm, right? So there. So it's going to be, I drew this backwards. So should cross this out. So basically on the high end, you're going to have 11.99 volts, right? Because that's for 10 amps through 1 milliohm. You're going to get that. And then 40 amps through 1 milliohm is going to give you 11.96 volts. Yeah. Right. And so your voltage at the GPU is going to be pinging between these two levels based on the amount of current flowing through the wire. Now, if we crank the wire up to 20 milliohms on both ends, what's going to happen is the combined resistance is going to be 10 milliohms. And, well, 10 amps through 10 milliohms is going to be 11.9 volts. And 40 amps through 10 milliohms is going to be 11.6. And yeah, the capacitors on your GPU and your voltage regulator, it's going to be thrilled about it. This is going to be loving life. Just amazing having this kind of, power delivery to it. So this is bad, right? Like there's a reason why, like actually arguably because the goal of the 12-volt high power connector is to carry so much current, the fact that they went with like 16 gauge cables is actually making it more susceptible to current imbalance because the resistance of the wire itself is extremely low. And you're also aiming for very low resistances in the actual connectors themselves. And so if one of the connectors is one of the connections is out of whack, or well, realistically, what needs to be out of whack is like 5 of them, because you need 5 of them to basically be bad, so that all of the current gets shoved through one, and then the one that gets all of the current is the one that's going to melt. But because you're aiming for this very high current, low resistance connection, you don't really have a lot of margin for the resistance to change much. So yeah, whereas like thinner cables with more resistance would actually kind of reduce that, but then the voltage at the actual GPU is going to be all over the place, so that's no good either. So yeah, so adding resistance to our wires is not, a desirable way of solving the issue. So the completely insane option is like, okay, we're going to split our cable again. Like, we're going to split this over here. And we're going to have 2 power supplies. Yep, that's right. We're going to just double the complexity. So now we got 2 independent 12-volt PSUs. Also, we're going to need forward voltage sensing. And now we're aiming at exactly 12 volts, right? So we are aiming for 12 volts here. And now what we can do is, let's say we're pushing 20 amps into the GPU, like consistent 20 amps. Well, that means we want 10 amps through the top line, and we want 10 amps through the bottom line. And if the bottom line has 4 milliohms on it, well, that's very simple. Here we need 12.04 volts, and here we need 12.02 volts. This is totally fine and not a design problem whatsoever. Also, God help you when that current draw suddenly drops. Because what that's going to do is it's going to do that with the current. I mean, technically, you can design the power supply, the top power supply to deal with that, but like, the power supply could be designed to deal with the fact that, like, hey, if the load ever drops suddenly, you're going to have 12.04 volts connected to 12.02 volts. That's going to shove current back into the PSU. The PSU can be designed to work with that. You probably don't want to have to design for that, though, if you could avoid it, because it's just like, why? Right? Like, so yeah, so this is the, like, other way you could try to current balance the connector, is by literally giving every single pin its own power supply, which is insane and a bad idea. So yeah, so that's why power supplies don't do current balancing, because your options are basically either you add resistance to match the resistance of the, like the differences in resistance of the pins of the connector, which requires some kind of monitoring circuitry so that you can detect a current imbalance, and then you need some extra circuitry to actually add that resistance with. And at the end of all of that, you've reduced the efficiency, like, of the power delivery to the GPU, and you've made the transient response at the GPU worse. Right, like the actual, like, voltage delivery to the GPU has gotten significantly worse. Or I should say, the voltage stability at the GPU is now significantly worse because there's a bunch of extra resistance in the connection. Lovely. And then your other option is like, okay, you build 2 power supplies and they just output slightly different voltages depending on how much difference there is in the resistances of the wires, which is also not great. So, yeah, that is why power supplies do not do current balancing for power connectors, because it's not a good idea. It's just not practical. It's not that it's impossible, it's just really not practical. And as far as I'm concerned, like, historically speaking, GPUs handled power balancing just fine. You would just, like, the simple example is Vega, right? So a Vega 64, if I remember correctly, was a 300-watt GPU. And the way the power delivery on that card works is it had a 12-phase VRM. And it looked something like this, where you had 6 phases above the core and 6 phases on one side over here. And basically, the way this thing made sure that roughly half of its power consumption was pulled from each of the 2 8-pins was that these 6 phases were hooked up to one 8-pin, and the other 6 phases were hooked up to the other 8-pin. And that was that. That was it. There was no other extra circuitry on there. It was really just like, yeah, 6 of the V-core phases were hooked up to one 8-pin, and the other 6 were hooked up to the other 8-pin. Now, yeah, and that's like, and the reason this maintains current balance is because the voltage regulator for the GPU is trying to keep current balance between the phases, right? So, and the reason the voltage regulator is trying to keep current balance between the phases is because that's optimal for power delivery efficiency. So even if this connector had slightly more resistance, okay, so this 6-phase would be getting, say, 11.9, I don't know, 98, and this one might be getting 11 point, okay, let's say 97, and this one might be getting 11.98, right? The voltage controller doesn't care because all it cares about is that Vega ran on what, like 1.2 volts? So let's say, okay, let's say 200 amps output current. So the voltage regulator is like, okay, I want 100 amps out of here and I want 100 amps out of here. Right, and as long as it's maintaining that, it will keep these two power connectors pretty current balanced. Now, NVIDIA GPUs, for reasons I will never understand, never have current balancing this simple. NVIDIA usually has like a whole bunch of auxiliary components for trying to shuffle phases between the two power connectors. But then, like, you know, as far as I can tell, that's like a design goal of NVIDIA is just like, why make simple power delivery when you can make complicated and broken power delivery? So we got a 12-pin power connector with 4 sense pins that don't do anything useful, and it has a tendency to melt. Amazing. Real design progress right there. And also, I'm pretty sure the 12-volt high power connector is designed the way it is, where it combines all of the pins into one big blob of 12 volts on the GPU, for the simple reason that NVIDIA didn't want to deal with all of the active current balancing circuitry that they were putting on their GPUs since, I think, the 600 series. If you look at any, and it's especially noticeable on 2080 Ti's, there's a ton of like extra small MOSFETs scattered around those cards whose only purpose is for shuffling which power stages are connected to which power inputs, which is just like, why is this even here? I've never seen an AMD GPU bother with this. Really old NVIDIA cards didn't do this. And then with like, I do actually know why they do that. It's because their current, like their power monitoring and power limiting is overly sensitive. But anyway, like instead of NVIDIA giving their power limit a little bit of headroom to work with, they went the complete opposite direction where the power limit is extremely strict. And so you need a bunch of active current balancing circuitry so that the GPU doesn't bounce off of its own power limit. And it's like, why? Just like admittedly, like AMD did screw up with, say, the RX 480, where they accidentally put a little bit too much vCore onto the PCIe slot, but like they were able to patch that with a literal BIOS update. Actually, I don't think it's even a BIOS update. They patched it with a driver update that basically just told the voltage controller to bias towards the top 3 phases that were hooked up to the 6-pin, which basically meant that the GPU would slightly overload the 6-pin rather than the PCIe slot, but yeah, NVIDIA, on the other hand, is like, no, we need to absolutely perfectly current balance all of our connectors, and I guess they got sick and tired of that, so here's the 12-volt high power connector. No more current balancing required. And you just have to, you know, hope that it doesn't melt. So, yeah. But anyway, so like current balancing the connector from the PSU side is just not practical. Like it just isn't. Yeah, I think like the better solution to this would have to just have a power connector with more headroom and laxer like power limit enforcement. Right? Because like I feel less bad about overloading an 8-pin power connector than like, because the thing is like the 8-pin has so much safety margin. Right? So it's like, oh yeah, like the Vega GPU might sometimes pull a little bit too much power from one of the 8 pins. But the 8-pin has so much margin that it just doesn't matter. Whereas with the 12-volt high power connector is like no GPU that NVIDIA has approved, as far as I know, is capable. Like if you just use the software power limits, right? Like if you're overclocking, you can't set the power limit higher than the limit of that power connector. And yet there's people who have, who've plugged plugged in a 4090, never overclocked it, and it still melts. or a 5090 never overclocked it, and it still melts because there's not much headroom, and the connector is extremely sensitive to not being plugged in just right. Which like, and to me, like the thing that's insane to me is like this is a piece of plastic, right? Like the connector is just a bit of plastic and some metal. Like why? Like why does it need to be so close to the limits? Right? Like you could just like respec it to 300 watts and just put 2 of them on there. And then I guess NVIDIA's problem is like, oh, but then we'll need current balancing. Just respec it to 300 watts with a momentary overload of 600. There. Solved. 300 sustained, 600 watt peak, and then you don't have to worry about making all of your current balancing super fast and accurate. Which is basically how old AMD GPUs and old NVIDIA cards work. And actually, even current gen AMD GPUs work, right? Like a 9070 XT still doesn't have any current balancing circuitry. Why? Because they just don't enforce a power limit that's as strict as NVIDIA is. Because, yeah, the 8-pin is not going to melt if you overload it by 30% every so often. Actually, it probably won't melt if you overload it by 200% for continuously. So, like, you know, and instead we get the 12-volt high power connector where it's like, oh, finally, we can get rid of all of that optional current balancing circuitry that we, for some ungodly reason, insisted on putting on our GPUs, and now the connector's a problem. It's like, you didn't need that current balancing circuitry in the first place, and the connector is a problem. Anyway, yeah, I am like, also, fun fact, motherboards don't have current balancing circuitry if they have multiple 8-pin power connectors or multiple, like if you have like an 8-pin and a 4-pin, your motherboard doesn't distinguish between them. They're wired in parallel. And again, you don't really hear about that melting either, even though it would theoretically be susceptible to the exact same kind of failure mode as a regular, 12-volt high power, or like the 12-volt 2x6 and 12-volt high power connector. But you don't hear about those melting because they just have a bunch of headroom. Right? Like, if you use an underspec'd connector, you can mistreat it and it's like, it just doesn't care. But NVIDIA is like, no. Like, they babied the 8-pin and the 6-pin on their GPUs for years and years and years. And then we switched to this 12-volt high power connector where it's like, oh yeah, we took all of that safety margin that the old connectors had, and we just threw that right out the window. Also, we got rid of all of the current balancing. And not just the optional stuff, all of it. So you better hope that you plug in that connector just right, because if you don't, it might melt. And if you're lucky, you'll only find out when you go to unplug it when you're upgrading your GPU. Which I guess is going to ruin the resale value of your card on the second-hand market because, like, somebody's going to have to dig the plastic out of that connector. Huh. So, because that's a funny thing. I actually do remember reading an article about a reviewer or something, like some kind of tech website, where they had a 4090 that ran for like 2 years or like a year, I don't know. But it was like a really long period of time without them ever unplugging the connector. And then when they finally went to unplug the connector after the most recent round of 12-volt high power connector drama, they found out that it melted and it just kept running for several years because, like, yeah, like, personally, I don't think the connector is like a huge fire hazard. I just think it's stupid that, like, your very expensive GPU can end up with a bunch of melted plastic in its power connector because they couldn't be bothered to design a proper power connector. Like, it's a $2,000 GPU. Do you really need to cost optimize the power connector? Of all things. And again, this is NVIDIA. Like, they wouldn't put a $0.2 fuse on a card if they don't have to. And they don't. So, yeah. Well, funnily enough, they did have all of that current balance. Though I am convinced that all of that current balancing circuitry on NVIDIA old NVIDIA GPUs is NVIDIA's own, like, that was a problem of NVIDIA's own creation. That wasn't like, oh, we're like adhering to the spec. No, this is just like we've made a problem for ourselves and this is how we're solving it. Um, but because yeah, AMD cards never bothered with that, and they still don't bother with that, even though they now have shunt resistors. So it's just like I don't know what like NVIDIA things. Um, Anyway, that's it for the video. That went completely off track towards the end, but hopefully you now understand why power supplies don't try to current balance your power connectors, because it really isn't practical. And it should just, like, and if something is going to be current balancing the power connectors, it should be the device pulling the power, right? Because there you have more switching regulators, so it's actually really easy to do the current balancing because you have like downstream on the downstream voltage regulator. That's where you can easily deal with the current balancing issues instead of trying to deal with them upstream. Um, so yeah. Um, anyway, that's it. So hopefully, if you found this somewhat interesting, and maybe even useful, though I don't know how, then wait, I'll just do the typical outro. We'll start over. So thanks for watching. Uh, like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support the channel, there are links in the description that you could check out. It would be very much appreciated if you did. And that's it. So thanks for watching, and goodbye.